All right, so we're using the first derivative test to find what? Local extremes, right? All right, so y prime is, let's do product rule, 1 d2, so we have 1/2 times 8 minus x squared to the negative 1/2 times negative 2x, right? Plus 2 d1. Okay? So just that looks pretty monstrous. So negative 2 times 1/2 is negative 1, and then we have negative x squared over 8 minus x squared square rooted plus 8 minus x squared square rooted. We want to know when that equals 0 or does not exist. So first of all, can this ever not exist? When the denominator, right? When that equals 0. Do you agree?
Yes.
Y prime equals 0 when, so I kind of split it into 2, okay? When negative x squared over that
Equals negative 8.
Okay, fine. Equals negative square root of 8 minus x squared.
So multiply to both sides.
Okay? First of all, let's deal with this. If I square both sides, 8 minus x squared equals 0. So x squared equals 8. So x equals plus or minus the square root of 8. Right?
Yes.
Okay, over here, what should we do? Can we get rid of the negatives?
No.
Why not?
Okay.
Okay.
So you're gonna have x squared equals.
Do you want to cross multiply?
Yeah.
So x squared equals 8 minus x squared. Right? Because if you do this times this, you have two square root. When you square a square root, the square roots undo each other, right?
So then you bring the x squared to the other
So you have
side.
2x squared,
Equals 8.
because there were 2. Okay. Minus 8 equals 0. I would always rather use factoring and using the zero product property when possible.
Oh.
Although you don't have to, but I think it's better.
Can't just solve for x?
That's what we're doing.
Oh. So what if you just like divide by 2 and then like just square that?
Over here, if you had instead done this, that's fine, long as you know
It's plus and minus.
plus and minus. Okay? So how many critical values do we have? Critical points. 1, 2, 3, 4. Do we not? Okay, let's see. Oh, sorry. What? Did you guys all do this problem? Did we get this far?
Are we always supposed to do that? Like split it up into 2?
Yes, because critical values, remember, critical points, CPs, can happen either when the derivative does not exist or when it equals to 0. So letting it equal to 0 is not enough. You'll also have to think about when it does not exist. The examples I gave you earlier were polynomials, so they never had a situation where it didn't exist. That's why we didn't check those other ones. Okay? So technically, if we were going to make that chart, you guys, how many CPs do we have? 4. X equals negative 2, x equals 2, x equals negative rad 8, x equals positive rad 8. Why? These guys, because here f prime of negative 2 equals 0, f prime of 2 equals 0. Here f prime of negative rad 8 and f prime of negative positive rad 8, those do not exist. Or undefined. That's why. Okay, so we have 4 CPs. But the goal is not just to find CPs. We're going to use our knowledge of CPs to invoke the first derivative test, right? Why do we want to use the first? Well, the problem told us to use the first derivative test. What does the first derivative test help us to find? The local maxes and mins. So let's make a sign chart, okay? So we plot our critical points. Which one's bigger, 2 or rad 8?
Rad 2. No, rad 8.
Well, what's 2 squared? 4. So square root of 4 is 2. Square root of 8 is bigger than square root of 4. It's a little less than square root of 9. So, all right, so negative rad 8, negative 2, positive 2, and positive rad 8. Those are my 4 CPs. Okay, it's okay if it's not scaled. That's not the point. Okay, what is the point? To use the first derivative test. So what should I do? I'm going to plug in some values. Over here, I'm going to take like negative infinity, some really big number, and I'm going to plug it into which equation?
F prime.
F prime or y prime. If I plug a number that's bigger than square root of 8, whoa, can I even do that? No, because look, it's not part of the domain. Like, okay, try like negative 10. If I do 8 minus negative 10 squared, I'm going to get 8 minus 100. So I'm going to have a negative in the square root. So you know what? This part is not even part of the domain.
But the 8 is negative, so it's in terms of positive, so you add it?
No, because it's squared.
Yeah, but you have a negative square root of 8.
Yeah, you have. No, that's what she's saying. Anything to this side of the 8 is not in the domain. So the 8 is an endpoint.
Yeah, so the domain of this function, basically what is the domain of this original function?
Negative square root 8 to...
So basically this function is this, right? And what is the domain? It's important always. And that's kind of a thing we don't always think about, but we do need to.
It would be negative square root 8.
Good morning, teachers and students. Please pardon the interruption. This is an announcement regarding lunch today. We are going to go ahead and allow students to go outside for lunch today, as it is not currently raining, and the forecast indicates that it won't rain in the next hour or so. Should that change, we will go ahead and open up the classrooms and provide a warm, dry location for our students. But as it stands right now, we're going to go ahead and let the students out for lunch when the bell rings. Thank you.
Okay, so do you guys see how the domain of this function starts at negative rad 8? No.
Yeah.
Yes, at negative rad 8. Do y'all agree with me?
Yes.
So that means when I draw my chart, I don't even need to start here. I just start at negative rad 8. Okay, so can you give me a number between negative rad 8 and negative 2?
Negative 1. 0.
Negative 2.1. Okay.
How about 0?
No.
Oh, wait, no.
Okay, so if I put in negative 2.1 and I plug it into the first derivative, this is going to be
negative 3.
positive, negative.
No.
If you were to plug in 3...
If you were to plug in negative 3, you get 8 minus 9.
Yeah, and that's a negative
You get
2.
square root of a negative.
I know that we can't put in 3 because 3 is...
Oh, because 3 is past.
Mm-hmm.
Oh.
So this one, you know, it might be kind of difficult to know if it's positive or negative. I would actually use a calculator, okay? Because look, when you do 2.1 squared, is that going to be bigger or less than 8? Less than 8. So this is going to be a really small number, okay? But if you square root that small number, it's going to be even smaller number.
Yeah.
And then you're going to have that number squared, okay? Like 2.1 squared is like 4.2, right? But it's going to be negative divided by a positive number, a small positive number. Yeah, so this is going to be a negative number plus a positive number. So when you're adding negatives and positives, you don't know really if it's going to turn out negative or positive unless you know which one's bigger. But based on the numbers that we just used, which one do you think is going to be bigger, this negative number here or the positive number?
The negative.
The negative. Because you're going to have a number divided by that really small number. So this number, so this one, yeah, so this is a big negative number. So here it's going to be negative. If you didn't get that, just take your negative 2.1 on your calculator and actually just plug it in, okay? This one is nice because, I could just plug in 0. If I plug in 0, I get negative 0 plus square root of 8.
So it's positive.
It's going to be positive, right? If I do this here, is anything going to change? It's going to be the same process here. I could do positive 2.1. And the negative didn't matter because it got squared away. So, here we go.
So then you wouldn't count anything past the...
Oh, I was wrong. The domain ends here too, right?
Yeah.
So, I was wrong about the domain. The domain is not negative 8 to infinity. It's negative rad 8 to positive rad 8. My bad. Okay? So, what's going on with the graph? Based on the first derivative test, we know that the graph is decreasing, increasing, and decreasing again.
So it only has 3.
So, where is the min?
X equals -2.
Right here. And the max is?
2.
Right here. And you guys would use a full sentence to describe that, right?
But what about the endpoint?
The end, those aren't math.
Those,
aren't
okay, well, that's a good, no, that is a local min. Okay, that's a very good. What about right here? Is this over here, because this is an
Where do
endpoint?
you have to plug it in to know what it
Oh, no, we're not talking about absolute.
Oh, that's
We're talking about local. So at least in this area, this guy over here is taller than everybody else over here, right? So this is going to be a local max. Is it not?
Yeah.
What about over here? We don't know that. Because we don't know if it's like this or like this. You see? See that? All we know is it goes up and down and up and down.
There's 2 local mins and maxes.
Okay, hold on. What about here? Yeah.
Okay.
This is a min. Okay? So max min. But we don't know. How would I know if this is actual global max or a global min?
By plugging them in.
By plugging those x values into what?
The original.
The y or the original f, and then compare all the y values. Okay?
That's why it's negative.
So that's why the answer said that there's 2 local maxes and there's 2 local mins. And then you're supposed to support your answer. I don't think anybody did this, did they? Support your answer graphically. That means make a little sketch. Okay? Oh, it said to identify absolutes. And so they told us, actually, why 4?
Oh, because when you plug it
The absolute max, is it the x value or the y value that's the max?
The y value.
It's the y. So this one is an absolute min, and this one over here is an absolute max. Once you plug them in. So that's why they give you the x and y, because we're testing to see which one's a local and global. So based on that information, did it look like this or like this?
Okay, I don't remember the...
Okay, the points. So at negative rad 8, the y output is 0, and then it goes down to negative 4, and then it goes up to 4, and then it goes up to 0.
Oh, okay.
So, okay, let me write that down here. So the y values here are 0, negative 4, 4, and 0.
So what would be the second one?
So we go to 0, negative 4, 4, and 0.
Yeah, second
So it's this one, right? 0, negative 4, 4, and 0. So that's why this is a local and global max, and this is the global min. Does that make sense? Now all of this is a lot of work that should have gone into you doing number 5. And when you go ahead and sketch, do you see why they want you to do a sketch? So you could kind of see the big picture and kind of tie it all together. Okay? All right, questions? Okay, so, oh, that was just one problem on the homework. Okay, so let's look at 29. We're going to get into more of this graph stuff. Well, we were supposed to today, but I think we're going to get to it tomorrow. Yeah. Okay, so 29. Oh, okay, no, we were supposed to tomorrow. In the graph of the function, blah, blah, blah. Okay, the graph of the position function. You know the S is usually used for position, right? Oh. Okay. What about 57 and 44? Were those also from the other page?
Yeah.
Those are in the first page.
What about 44? Oh, all of them are from the first one?
Yeah, it was only
Page
5.
205, right?
202.
Okay. 20. 9. Find all possible functions with a given derivative. That one?
Yeah.
Okay. So remember, that's the whole thinking backwards thing. So if f prime of x equals what now? X. Think about what the function has to be for the derivative to come out to be x. Well, remember the power rule says that you always power down. So to go backwards, you have to power up, right? So maybe it's a quadratic, right? But if you do the derivative of x squared, what do you get? 2x. But we don't want 2x, we want just x. So we had to multiply that by 1/2 or divide by 2. You see that? So now let's try it. If you do the derivative of that, you're going to get 1/2 times 2x. Hey, and that's what I wanted, right? Does that make sense? But what are we forgetting?
The constant.
Where do I put the constant?
After that.
After which one? F prime or F?
F.
F. Why? Because there could be any number here that's a constant, because once you find the derivative of the constant, it's going to be 0. Good. Okay? 44. What velocity will you hit the water? With what velocity will you hit the water if you are diving from a 10-meter diving platform? With what velocity will you hit the water if you dive off the platform with upward velocity? This is going back to the last chapter a little bit. And I'm going to save this one for after school today. Please remind me. No, I'm serious. Oh, okay. Because we really have to do the second derivative test, and this is going kind of back. 57. Oh, it's a quickie. Oh, yeah. Let's save that one for another time as well. I'm going to write it down. Please remind me, because sometimes I'll forget. 57 and 44. Okay. Second.
Your answers, for 57, your answer says like 1.3. What if we put like 1.25?
You have to be accurate to 3 decimal places.
Because the graphic gives us 1.25.
Okay, I'll look into that. Okay, for number 57?
Yeah.
Okay, I'm going to skip example 4, you guys. Does that magnet bother anybody else?
Yeah.
Somebody move it.
I thought it was like a mark.
Okay, so, alright, I'm not going to do this because you guys could go back to the video, refer to the video if you want, but because it's more repetition of what we know. Find the inflection points. It's a little different. It's almost the same thing as finding the concavity, but what's an inflection point again?
Where the concavity changes.
We're called the concavity changes. Okay, so you're doing the same process. Find the first derivative. The first derivative of this is chain rule, 2 times this e times the derivative of that exponent, right? Then I do that again to find the second derivative. Okay? No, it's okay. Don't copy it. Just kind of look at the process. Once I find the second derivative, I figure out, hey, does that second derivative ever equal 0? Never. Oh, no. Sorry. This part. Does this part ever equal 0? No, because e to the anything will it will never be 0, right?
Yeah,
So that's never. This part, does that ever equal 0? Yes, at plus or minus rad 2. So now I have 2 possible points of inflection. I plug in to the second derivative to see that it goes concave up, concave down, concave up. So where's the point of inflection? Right here where the concavity changed from positive to negative, and again here where the concavity changed from negative to positive. But my final answer is going to be, because they asked me for the point, so I'm going to take the x value of my 2 inflection points and then find the y value to find out where my inflection points are. Okay? Is that okay, Sky? All right. Now this is what you need to write down.
Oh, we haven't learned the second derivative.
That's what we're about to learn right now. Okay, so please write this down. The second derivative test for local. So remember, this section is all about how can I find local maxes and mins. There's 2 ways you can do it. One, you could do a first derivative test. But you can also use the second derivative test. If you think about it, the second derivative test is easier, kind of, but we usually use the first derivative test. It's more popular, but sometimes the second derivative is just much easier. Okay? Kind of.
This is all for local, right?
Yes, it's all for local.
So for the first one, you would find the critical point?
For first derivative test?
For the,
Yeah.
It would just be the critical point, and then for this one, it's going to be the points of inflection?
Possible points of inflection.
Possible.
No, it will not be the point of inflection. You still have to find the critical point. You'll see. Point of inflection is usually not.
But that's just for concavity.
Yeah, it's for concavity changing. It's still the critical points. It's critical because it could actually give you a local max or min.
Wait, does that say at capital C?
Yes. All right. Did you guys write it down? Okay, I want you to think about what this means. Okay? First of all, we already know from what we talked about up till now that if there's going to be a local max or min, that's pretty much like there's going to be a turning point, right? At a local max, the first derivative is always 0, or it doesn't exist. Okay? Because it could also look like this, right? And at a local min, also, right? It has to be a critical point. Do you guys agree that a local max or min has to be at a critical point? Sometimes there's a critical point.
On the end point.
No.
Oh, no.
Sometimes there's a, oh yeah, that's, the endpoints are special cases. Sometimes there's a critical point, but it's just a saddle point. Okay, so sometimes a CP yields a local max or min, and sometimes it yields nothing. Okay? No local max or min. Okay?
Wait, Miss Han.
Yeah.
On the AP test, can we write, like, if it asks, like, find all the points where f prime is 0, can we write, like, even though if it's not a local min or max, can we write that it's a saddle point?
If it just asks you where f prime is 0, yes.
Oh, okay.
But if it asks you if it's a local max or min, then no.
Okay.
Yeah. Okay? You guys still with me? If you think about it, if you have a critical point, so that's this, or this, or this, or this, or this, and you test the concavity, the second derivative. What is the second? I'm going to do the second derivative in red. Okay? What's the second derivative here at C?
Negative.
Because it's concave down here, right?
Yeah.
So the second derivative is going to be negative, right? You agree?
Yeah.
Does everybody agree, or just Arlene? Okay. So think about this graph. What's the concavity of this graph in this whole area, in this whole interval?
Negative.
The concavity is concave
Down.
down. Remember, the bowl is going down. Okay? So that's the f double prime would be negative. What would f double prime here at C be?
Positive.
Positive. So f double prime would be positive. Yeah?
Isn't it also because the slope is like decreasing?
The
'Cause going
slope
from, like,
is
a 1
yep,
to,
yep,
like,
yep,
a negative
yep,
1?
yep.
So wait, at that point,
No, the whole graph.
At this, but at this point, the f double prime would be positive. F single prime would be 0, right?
right?
But f double prime would actually be positive because this whole area is concave up.
Oh,
Okay?
oh, the whole area to the right of it.
No, this concave up, concave up, concave up, concave up, concave up this whole time.
Right.
Okay? Same thing here. Oh no. Well, oh, this doesn't count because this is a critical point, but it has to be f single prime has to equal 0, right?
Wouldn't that be a positive concave?
Yeah, but don't worry about this right now because this, remember, second derivative test only matters. We can only use it if f single prime at c equals 0.
I thought it
Not
was
for the does not exist cases.
Oh, so for
It
the
has to exist
so
and
for
it has
the
to equal
does
0.
not exist, we would use the first derivative.
Yeah.
Okay.
So you can only use the second derivative test if you have this. Okay? What about here? F single prime equals 0. So it is a critical point. But what is F double prime here?
Still positive.
It's going to be 0.
Why?
Or because there is no concavity here. The concavity goes from negative to it's a point of inflection. So the concavity is going to equal 0. Okay, hold on. Where are you
So
going?
the concavity on.
This is not the time to stretch.
Keep going.
Okay, so
4.3b?
that's why we can use this. Yes.
No, it's 4.3b.
Yes. Yeah. That's why we can say, if I found out that there's a horizontal tangent here, and the second derivative is negative, then it's going to be a max. Okay? There's a local max. If the first derivative is 0, there's a horizontal tangent, but the second derivative is positive, then it's a local min. It's kind of counterintuitive, right? It's the second derivative is positive, so it's a max. The second derivative here is negative, it's a max. When the second derivative is positive, it's a min. Think about it like this, you guys. Oh, that's the opposite. Okay. So think about it like this. Hold your hand like this. Is this concave up or down?
Up.
So is this a max or a min? Min.
Oh.
Now like this. Is this concave up or down?
Down.
And so is it a max or a min?
Max.
Okay. That's the second derivative test. Okay?
So the second derivative is based on the whole thing as a whole.
Yes.
So does it
So
have to do with the derivative, the f prime, like the first prime? It doesn't have to do
well,
with
you have to first find that f prime of c equals 0.
the sign of the derivative doesn't necessarily affect whether it's concave. Like,
The sign of the first derivative is going to be nothing because it's 0. So you guys, I wanted to show you one example. I'll go ahead and take a picture of it and send it to GroupMe. If you're not on GroupMe, text one of your friends and get it from them, okay? So your homework, hold on you guys, hold your horses. Your homework is the next one.
Boys and girls basketball is today at Gus Resler. Girls play at 4 and the boys play
That
at
one.
5:30.
Okay?
The address is
Video test. See you after
2023 Union
school.
Avenue near Adams and
You have to
Hoover.
come after
Please
school.
come and support your fellow Eagles. Thank
Well,
you.
you have to see it after school, okay? You have to, I can't give it to you to take home. Yeah. Bye, guys.